Hi, so welcome for the first online practical session. Okay, we will be discussing online how to do all these practicals. And when you come back to the college, you can do it by yourself. The instruments will be provided to you, and especially for this particular experiment, even the connections will be done. So all that you have to do is come and take only the readings and maybe do the calculations also. Of course, you can even use the calculations that I have given in this particular experiment also for yourself. So this is a very important session. Watch it carefully because you will be using this as it is, as I will be performing here in the experiment, you will be performing in the laboratory. Okay, but before we go ahead in the laboratory, let us check out some of the basic things that you need to know about. So first of all is the aim. Okay, first of all is the aim, and the aim is to study the Hall effect. Okay, so if you remember from the theory class that I took, I had explained what is Hall effect. Okay, that if you have a current and magnetic field perpendicular applied perpendicularly to the semiconductor, then there is a voltage that is generated, and this voltage was called a Hall voltage. So we are going to actually see that there is a Hall voltage Hall voltage actually generated here. Okay, and using this Hall voltage we are going to calculate a very important coefficient, a very important value called the Hall coefficient, that is RH value. Now RH value, if you remember from your theory, if it is positive, then the conduction in that particular sample is due to hole, and if it is negative, then it is purely due to electrons. Fine. Now you will be given an apparatus like electromagnet. You will be given a power supply for electromagnets, Gauss meter to measure the magnetic field, and Hall probes. Okay, Gauss meter with Hall probes. Okay, Hall probe, I'll just show you. I have them all. And Omega Hall effect setup. Omega is the name of the brand. Okay, and Hall effect setup. A p-type or an n-type semiconductor. We have given you a p-type. Germanium semiconductor, we have given p-type, because answer that you will get is a positive one. And multimeter, in this case we are given you multimeter because in the Hall effect setup the display is not working properly. So just to get since the display is not working properly, we are given an external multimeter to take the readings of the current and the voltage. Okay, voltage that is developed. All right, and of course I do not know why I have repeated. I've already told you we are using electromagnets. Okay, the formula for Hall coefficient is RH is equal to Hall voltage that is generated. Z is the thickness of the specimen. I is the current that you will be giving. Okay, H is the magnetic field that is applied again by yourself, and we have to calculate all this in cubic centimeter per coulomb unit. Fine. Okay, look at this formula. The unit that you will first get is in terms of volts. Z is thickness, so centimeter, volt, centimeter per amp per Gauss. Okay, so this is the unit that you will get. You will have to convert it to cubic centimeter per coulomb. Fine. All right, so we will see that it's very simple conversion. Moving on, principle of Hall effect already discussed during the class hours. Okay, that is when a current carrying conductor or a semiconductor, we are dealing only with semiconductor, not conductor, okay, is introduced to a perpendicular magnetic field. Okay, a voltage can be measured at the right angle to the current path. Okay, so there is a voltage that is generated right angle or perpendicular to the magnetic and the applied current. Fine. And the effect of obtaining the measurable voltage known as Hall voltage. Okay, fine. So that's a Hall effect. Okay, or Hall voltage or Hall effect. Moving on, this is the setup that you will see in your laboratory. You will be given a digital Gauss meter. You will be given a Hall effect board, and you will be given a power supply. Okay, current power supply, which can be used to power your electromagnet, which is given here. Okay, this is here on these two corners there is a rotator which you can use to move the magnet closer or away from each other. Fine. And if you see this is a wooden stand that is given to you, on which you will be placing your Hall probe and the germanium crystal. Fine. So have a closer look at it. This is the Hall probe. You can see there is a small red color stick that comes out, which will actually sense the magnetic field. Okay, and this magnetic field which this is connected to the gauge meter, and will measure the amount of magnetic field across the what do you say, the electromagnet. Fine. Now look at this. This is what is given to you is the germanium crystal. You can see this in the center. There's a small germanium crystal, and across it there are 4 probes. You can see that 4 probes are there. Now these 4 probes are connected to 4 wires. The red ones, okay, the red one which you can see, rather orange one, is connected to the voltage, and the green one is connected to the current. Okay, so you can see perpendicularly it is there. All right, so the 2 probes from here and here is connected to the voltage, and here and from here it is connected to the current. So current will be perpendicular. This entire setup will be then perpendicular to the given what do you say, the electromagnet. Okay, and there will be a voltage that will be generated, and this is that wooden stand. Here you can place your on this you can place your gauge probe, but I would prefer you to use your hand only for this particular purpose. And this small edge that you can see here at the corner here, okay, is for placing this crystal, germanium crystal. By the way, this is the front and the back side of this same thing. Okay, so germanium crystal is placed here, small, and there are probes perpendicular to it, and you can use it for placing here on this edge. Fine. Okay, next, having a closer look at each of these gauge meter. Okay, you can see gauge meter, there is a button here which you can switch to 1x, 1x and 10x. So all the measurement that you will get on the display is in terms of gauge. So whatever readings you get, if the knob is on x1, then it will be just the same reading that you will write down, because whatever the readings multiplied by 1 will be the same reading. And if this probe is on this side, then it is multiplied by 10. So whatever reading you will get here will have to be multiplied by 10. There is a 0 edges that is given here. Now sometimes when you keep the gauge probe outside, even if it is away from magnetic field, it will show some readings here. Okay, and to adjust that you can use 0 edges and make it 0, and sometimes it might not become 0, and whenever if it does not become 0, then whatever readings you get, you will have to either add or subtract to it. If it is showing negative, then you will have to subtract, and if it is showing positive, you will have to add to the reading that you are getting here. Fine. Next is you have the Hall board. This is the Hall board. You can see Hall board has a knob here. Okay, can I erase this? Is there an eraser? Oops, sorry. Okay, so if I use this, yeah, there is an eraser. Just let me wipe this off and again go back to the pen, Control P. All right, so this is the Hall board, and here I have, yeah, so this you can see is for current and for voltage. So this knob, if you put on the current, you will get current, and if you go to this side, you can get the voltage. Fine. But now this knob is of no use because this particular display of ours is not working. So we'll be connecting from here to the multimeters, and we'll be getting our readings. Okay, so the current can be adjusted with this. We'll be giving a 5 milliamps current to the germanium crystal and measuring the voltage for different magnetic field that we have applied. Fine. And lastly, we have the constant power supply. Okay, this is very easy. The 2 probes from the electromagnet will go to the positive and the negative terminal, and the current that will be varying here is now discussed in the experimental section. Okay, and this is the current control knob, and that's it. Not much here. So we are done with the basics of what you need for the experiment, and I think it's now time to go to the laboratory to perform this experiment. So see you after the experiment is done for results and discussion. Hi, so we'll start with the practicals. That's on Hall effect. Okay, and as I've already explained to you the theory why we are doing this experiment, and about all the setup has been already explained to you in the theory. So I can straight away, theory means the part before this, so I can straight away start with the experiment over here. Fine. So as I've told you before starting this lecture, you are given this Hall probe to measure the magnetic field that you will be having across these 2 electromagnets that is given to you, and then you also have the germanium. Crystal given to you, which is connected across the current and the voltage. So we will be supplying the current and we'll be keeping it perpendicular to the magnetic field, and the voltage generated across it will be recorded, which you'll be able to see here in the um, machines that's given to you. So this is the power supply given to you, which is connected to the electromagnet. So more we increase the power supply, let us keep it at 0 initially. So I just keep this power supply at 0. So right now you can see the reading on the power supply is 0, which is connected to the electromagnet, which will be generating the magnetic field across this. All right, and whatever the magnetic field is generated will be then recorded here. So this experiment has two parts. First is for given current, how much is the magnetic field generated. So what we have to do is we have to give current in terms of 0.5, 1, 1.5 to 2.5 amperes, and check out how much magnetic field is generated in this Gauss meter using the Gauss probe in the Gauss meter, and note it down, because in the second part we are not going to check the Gauss meter reading. Okay, we are going to only set those current, and obviously that much of magnetic field will be generated in the electromagnet. Fine. All right, so then we are in the second part, we are going to use a Hall effect board which is connected to the germanium crystal. All right, to the current and the voltage. So I'll come to the second part in the second part itself. Okay, so first we can start with the first part, that is measuring for a given current how much magnetic field is generated. Fine. All right, so we can start with the Hall probe. As you can see, the Hall probe is quite far off from the electromagnet now, and if you see any reading in the Gauss meter, you need to adjust it to 0. So we have tried to set it to 0, the 0 Gauss, and initially while taking the reading, let it be on 1x. Okay, and then as the or number of as the you increase the current, as the amount of magnetic field that is generated increases, we will shift it to x10. Okay, multiply by 10. So let's cue some current now, that is 0.5 amps, and note down how much is the magnetic field. Here we have now set it to 5 amperes, and we are now going to use the Hall probe, okay, to measure the current. We are going to just place it. I hope you can see in the inset of the camera used here how we are using this Hall probe to measure the magnetic field, Gauss meter, measuring the magnetic field. So what you do is just try to rotate it a little bit slightly and check what is the maximum magnetic field that you can record. So as I'm rotating slightly, be very slow. Okay, and as I'm recording it very slowly, the maximum that I could record here is 643. The maximum reading that I saw is 643. So let me just note down this. For 0.5 amps, I got 643. And of course there was no it was adjusted very well, the 0 adjust is very well, so no need of adding any kind of a magnetic field. In case your 0 adjust is not coming proper, and even after adjusting the 0 current, if your Gauss meter shows some reading, then remember you need to add that much of reading to the maximum reading that you have observed. Fine. Okay, moving on to the 1 ampere. So we have set the current to 1 ampere now. We have set the current to 1 ampere. All right, you can see that the current is now set to 1 ampere, and we will now measure the amount of magnetic field for 1 ampere. And just adjust it a bit for 1 ampere. All right, so check out what is the maximum that you can get for 1 ampere. So it's 1208, 9, 10, 1210 to 12. Fine, the maximum that I recorded was 1212 for 1 ampere. So 1212. Let's increase, go ahead and increase this to 1.5. So now the current is set to 1.5 amperes, and we do the same reading. We'll check out how much is the magnetic field maximum that we can get. So 1762, 1755, 1797, 1798, 1799, 1800, 1804, 1805, 1806, 1807, 1808, 1808. Okay, 1867 also I saw. So 180 to 11. Okay, so let me take 1811 for 1.5 amps. And then we also go to 2 amps. So for 2 ampere of current, we have, okay, as you can see now the reading is going above the scale. Let me just check. Yeah, so now it's a time to shift this to the next knob, that is multiply by 10. So whatever readings that you will get now has to be multiplied by 10. So the maximum reading that I get here is 1995 is what I had got. 1917. One nine nine seven was the highest reading that I recorded. Fine, so let me note down 1997 and then multiply by 10. So 970, increasing this to 2.5 now. Increasing this to 2.5, that's our last reading. So for 2.5, okay, let's check out what is the magnetic field. So we are trying to adjust it to 19131752, and then we have also 16955. We're having trying to adjust it. Okay, it's not going more than 19 for 2.5. What we'll do is we'll take the 2 amp reading once again. Let's check out what it was for 2 amperes. So 1966. Okay, it looks fine for 2 amperes, 19970. Let me just again go to 2.5. So nothing wrong in 2 amperes. Just that maybe the sensitivity for 2.5 has gone bad. So 2.5. Let me check once again. So it is now going to be 19. So since our Hall probe is not able to detect beyond 1.2.2 amps, I mean it is detecting some readings, but obviously the magnetic field should have been much greater than that what it was at 2 amps. That's what we are not able to see. Okay, so what we could do is possibly not take the 2.5 amp reading, okay, and straight away go for the part 2. Okay, so in part 2, since we are done measuring the magnetic field, we can now keep the Gauss probe aside. We don't need it. Also, we can bring the current back to 0. We can bring the current back to 0. And after bringing current back to 0, I think we can just switch this off. We are done with the Gauss meter. All right. Now what we will need is a Hall effect board. A Hall effect board has a current input, okay, that you will be giving, and at the same time we also have the voltage. Fine. Okay, so we have this Hall probe which is to be connected. We just put it back. So what do we do is there's some problem with this display here, so we will be taking readings from the multimeter. Okay, so I'll be adjusting my camera now towards the multimeter to take the readings from the multimeter as we are adjusting the current. And what we need to do is we need to give an input current. The input current given through this will be 5 milliamps. So if I switch this on, okay, and also let me put on the multimeter and this one. Okay, 200 milliamps, millivolts. So this particular. So let me adjust my camera for you for the to see how it looks through the voltmeter. Yeah. So I hope the voltmeter is visible now to you. Okay, and is the reading of the voltmeter also visible? Yes, I can see the reading clearly. So you can also see that. So this is the voltmeter. This is for the current input, and this will be the voltage that will be giving. Current is in milliamps, voltage is also in millivolts that will be calculating. So procedure is very simple. We have this probe. I will also explain the how the germanium crystal is connected, okay, and for this experiment how we are going to give the current. We are going to give the current input of 5 milliamps. So we can just switch this on, and if I can switch this on and switch this knob to current, okay, towards the current, and then give 5 milliamps. So adjusting to 5 milliamps. Okay, so roughly 5 milliamps we are getting, but let me see if I can adjust it to much better. Okay, so this is 4.6. Okay, I think this is fine enough. 4.8, and now little more, 4.84, 5.3. okay, so this is fine. This is 5 milliamps of input that I'm giving. All right, and let me turn the knob to voltage, and we are going to note down the voltage that we are going to get. Okay, so for that we'll now just put this crystal inside, okay, and see the crystal is right at the center of the magnet. Okay, you'll be given a special stand, a wooden stand, so that the readings does not get. If you're given a metallic stand, possibly it will interfere with the magnetic field, so you'll be given a wooden stand. Okay, so we have 5 milliamps input current, and we are going to now give the we are going to simply measure the voltage that we are going to get, okay, as we are increasing the current. So what was the current we had noted? Magnetic field we had noted. We had noted down the magnetic field for 5 milliamps, 5 milliamps. Then we had noted down the current for 5.5, sorry, not milliamps, 5.5, 1, 2, and so on. Okay, so for similar current that we are going to get here, we are going to note down the voltage. Fine. All right, so let me just increase this to 0.5. So this is 0.5 now. I do not have the camera now displayed to the this, but per 0.5 current is fluctuating a lot. Is around current, sorry, voltage is what I am noting down, not current. Okay, so for voltage, VH for 0.5 is, let me just hold on to it, or maybe okay, all connections are fine actually. Yeah, let me take the closest reading, that is, let me take the closer reading, that is 18.2. It's fluctuating very badly. It's 5.5 there, everything is correct. Okay, so input is maintained at 5 milliamps. Okay, fine, and there's no way out. This is fluctuating. Well, it's fine, but 5 milliamps. And let me take this closest reading. Wait for some time. Maybe I will take the lower side of reading that whatever I get, even though it's fluctuating very badly. I think I can go for. I do not know the reason for fluctuation, but I think I can go for 23, 20, 20, 19. It's changing very, very fast. So I will go for 23.9 because I see it repeatedly. And we go for the next reading, 1 amps. So for 1 ampere, the voltage has increased, and also it's fluctuating. Whichever reading I will see repeatedly, I would take that. Okay, so there's no reason that I know why it is fluctuating so badly. All knobs and probes are very fixed very tightly. Oops, what happened to the input current? Okay, 5 milliamps. Let me take the 0.5 reading again. Check. So 0.5 is okay. I think this is better. Yeah, I will go for a lower side of a reading for 0.5. It's coming to 14, 11, 9.7, 8.9, 8.8. The lowest I will take 8.8. Okay, I will go for the lowest 8.8. Let me increase it to 1 amp, and in this case also I will go for the lowest. So 1 milliamps is, go for the lowest, 22, 19.4, 16.9, 14.5, 12.4, 11.3, 11.4, 11.3. 11.3 is the lowest as of now. Okay, let me note down 11.3. Let me go for 0.5, 1.5. For 1.5, it's 13.8. 11.9, 11.5, 11.2. Okay, let me note down 11.2. Just wait. 11.7. Okay, let me just note down that 11.7. Okay, let me go to 2 amps. For 2 amps, okay, no, it's not exactly 2. For 2 amps, all right, it's 19.6, 18.8, 16.9, 13.1. Okay, let me note down 13.1. So that's it. With this, we have finished how to take the readings. Okay. Sorry about this. I could not help it out. It was fluctuating a lot, the readings. All right. But we have taken the reading that was visible maximum times, and the lowest on the lower side, to be on a safer side, we have taken the lower reading. Okay. So very simple. Remember, this experiment has 2 parts. Okay. One part is where you will be using the Gauss probe to measure the magnetic field at 0.5, 1.5 to milliamps of current that you're amps of current that you're supplying from the constant current power supply. And after that, you are going to measure the magnetic field, okay, on the across the electromagnet by turning the Gauss probe, okay, so that you get the maximum field that is available. After that, you're going to go to the second part where you're going to give the input current of 5 milliamps, and you're going to measure the change in the voltage as you are changing the current across the, or magnetic field rather, across this, because you have supplied the current and magnetic field perpendicular, and as per Hall's effect you are supposed to get change in the what do you say, the voltage, okay, so that you're going to observe. Fine. So let's note it. Let's now go back to the pen and paper and plot all the graphs that is required, and also calculate. Oh, there's no graph here, so rather you can just find out the Hall coefficient, and why Hall coefficient is important is also already discussed. Fine. Okay. So see you while doing the calculations. So welcome back. We have taken all the readings, and I'm using the same reading. As you know, I ignored the 2.5 reading, so I'm taking only these 4 readings of 0.5, 1 and 1.5 and 2. We had got this same magnetic field throughout, and these were all in Gauss, okay, and here we had got one reading which had to be multiplied by 10, and that's why it is 19,970 all of a sudden. And these are the Hall voltages that we measured from that. Okay, now the Hall coefficient is measured using this formula that I showed you before in the first section. Okay, and I've just done one calculation to get this 13.68 into 10 raised to 5 reading of Hall coefficient. To this you need to multiply 10 raised to 8 to convert the entire volt centimeter per amp per Gauss to cubic centimeter per coulomb. And similarly you do this measurements for the different magnetic field of 0.5, 1, 1.5 and 2, and add them all up, divide by 4, you get the mean Hall coefficient. Now if you Google out and check the Hall coefficient, you will find that this reading is quite good, okay, especially 10 raised to 3, and this reading is fluctuating for different instruments, and also the kind of magnetic field that they are applying. Most of them are applying kilo Gausses, okay, but still we are getting quite good reading in terms of that. But this is the aim of the experiment, to calculate the Hall coefficient, and which is quite decent and quite good, and also it is positive. Therefore the carriers in this particular germanium is a p type, that is it is a whole current which is the flowing in this particular given germanium crystal. Now also, in addition, since I had covered in my theory, but practically you need not, you can only calculate up to Hall coefficient, but since I had covered these things in the theory, you can even calculate carrier density, and you can also calculate carrier mobility. Carrier density is simply 1 upon the Hall coefficient multiplied by the charge of the electron, and that comes to be 8.3 into 10 raised to 14. Again, 10 raised to 14 per cubic centimeter is a very good value. And carrier mobility is the Hall coefficient multiplied by the conductivity. Conductivity is, you can find, of a germanium on Google, and it is 0.1. And if you use that, you simply get 573 centimeter square per volt per second is the mobility. And finally, the result, okay, it's a Hall coefficient. This is the one only that we are aiming for, and this is the aim of the experiment. That is, it is 7.53 into 10 raised to 3 cubic centimeter per coulomb. Okay, that much volume per coulomb. Okay, fine. So I hope the experiment was interesting and easy, especially the calculation part is very easy, and even taking readings is very easy. There were some glitches that we got because of instability of the reading in voltages, but then it's fine. You can just follow what was told to you during the experiment. Okay then, thank you, and see you for the next lecture.